Gravity is not a force. Then what is it? Tonight we're going to explore one of the most profound revelations in the history of science. We're going to discover that everything you've been taught about gravity is wrong. Not slightly wrong. Fundamentally, deeply wrong. Gravity, the force that keeps your feet on the ground, that holds the planets in their orbits, that governs the dance of galaxies across the cosmos, isn't actually a force at all. By the end of this journey, you're going to understand what gravity truly is, and that understanding will forever change how you see the universe and your place within it. Before we begin, if you enjoy these deep explorations into the nature of reality, a quick like or subscribe would really help the channel grow. Now let's embark on this journey into one of physics' most beautiful insights. Let's start with what you probably think you know. You've been taught since childhood that gravity is a force, an invisible force that pulls objects toward each other. The earth pulls on you, keeping you from floating away. You pull on the earth, though your pull is far too weak to notice. The sun pulls on the earth, holding our planet in its yearly orbit. Every object with mass, you've been told, exerts a gravitational force on every other object with mass. The strength of this force depends on how massive the objects are and how far apart they sit. Double the distance, and the force becomes 4 times weaker. It's elegant. It's mathematical. It's been taught in physics classrooms for centuries. And it's incomplete. The truth is stranger and more beautiful than anything you've imagined. Gravity isn't pulling you toward the earth. The earth isn't pulling on the sun. Nothing is pulling on anything. Instead, something far more extraordinary is happening. The presence of mass and energy warps the very fabric of space and time itself. Objects aren't being pulled along curved paths. They're traveling in perfectly straight lines through a curved universe. Your weight, the sensation of the floor pushing up against your feet, isn't because the earth is pulling you down. It's because the ground is accelerating upward to meet you as you try to follow your natural, straight-line path through curved space-time. This insight, this revolutionary reconceptualization of gravity, stands as one of the greatest intellectual achievements in human history. It's the centerpiece of Albert Einstein's general theory of relativity, published in 1915, and it represents nothing less than a complete transformation in our understanding of space, time, and the fundamental nature of reality itself. To appreciate how radical this idea truly is, we need to go back to the beginning, back to when humans first started wondering why things fall. Ancient understanding, from Aristotle to the medieval world. For most of human history, the question of why things fall seemed to have an obvious answer. Objects fell because that was their nature. It was as simple as that. The ancient Greek philosopher Aristotle, whose ideas dominated Western thought for nearly 2,000 years, developed what seemed like a perfectly reasonable explanation for motion in the heavens and on earth. According to Aristotle, the universe was composed of 4 earthly elements: earth, water, air, and fire, plus a 5th celestial element called ether that made up the heavens. Each element had its natural place in the cosmic order. Earth, being the heaviest element, naturally sought the lowest position at the center of the universe. Water, lighter than earth, naturally positioned itself above the earth. Air rose above water, and fire rose above air, seeking the highest earthly realm. The celestial sphere, made of perfect, unchanging ether, occupied the space beyond the moon, where everything moved in perfect circles for eternity. According to this view, objects fell not because of any force, but because they were seeking their natural place in the cosmic hierarchy. A rock fell because it was made primarily of the element earth, and the element earth naturally moved toward the center of the universe, which happened to coincide with the center of the earth. The heavier the object, the more strongly it possessed this natural tendency, and therefore the faster it would fall toward its proper place. This theory had a certain intuitive appeal. After all, heavy objects do seem to fall faster than light ones. Drop a stone and a feather, and the stone reaches the ground first. The theory explained what people saw with their own eyes. It also established a fundamental division in the cosmos. The terrestrial realm, the region beneath the moon, was the domain of change, corruption, and imperfection. Objects moved in straight lines toward or away from the center, but the celestial realm, the region beyond the moon, was perfect and eternal. The heavenly bodies moved in perfect circles, which Aristotle considered the most perfect form of motion. They neither fell nor rose. They simply were, forever tracing their ordained circular paths across the sky. Medieval scholars, working within the framework of Aristotelian physics, refined and elaborated these ideas. They debated the precise mechanisms by which objects move toward their natural places. Some proposed that the medium through which an object moved, the air or water, played an active role in the motion. Others focused on internal principles within the objects themselves. But the core idea remained. Motion required an explanation, and the explanation lay in the intrinsic natures of things and their relationship to the cosmic order. This worldview persisted for centuries, largely unchallenged, because it seemed to work. It explained what people observed. It fit with religious and philosophical ideas about hierarchy, order, and purpose in the universe. It provided a complete cosmological system that encompassed both the heavens and the earth. And perhaps most importantly, it didn't require the concept of force as we understand it today. Objects moved because of what they were, not because of what was acting on them. But cracks in this edifice began to appear. Careful observers noticed problems. If heavier objects fall faster because they possess more of the element earth, why do objects of very different weights sometimes seem to fall at nearly the same rate? Why do projectiles, when thrown, continue moving forward for a while after leaving the hand? By Aristotelian logic, once separated from the motive force of the thrower, they should immediately begin falling straight down. Yet they follow curved paths, continuing forward even as they descend. These questions troubled medieval scholars. Some proposed ingenious modifications to Aristotelian physics to account for these observations. Jean Buridan, a 14th century French philosopher, proposed the concept of impetus, a kind of internal motive force that an object acquired when set in motion and that gradually dissipated. This explained why projectiles continued moving after leaving the thrower's hand. But it was a modification, a patch to the system, not a fundamental reconceptualization. The ancient and medieval understanding of motion, for all its sophistication, lacked something crucial. It lacked the concept of inertia, the idea that objects in motion tend to stay in motion unless acted upon. It lacked the mathematical tools to describe motion quantitatively, and it lacked the experimental method that would allow theories to be rigorously tested against precise observations. These gaps would begin to be filled as the scientific revolution gathered momentum in the 16th and 17th centuries. But before we could arrive at the revolutionary insight that gravity isn't a force, science first had to convince itself that gravity was a force. That journey begins with an Italian mathematician who dared to drop things from very high places. Galileo and the foundation of modern physics, Galileo Galilei, stands at the threshold between the medieval world and modernity. Born in Pisa in 1564, he would grow up to become one of the founders of modern physics, not because he had all the answers, but because he asked questions in a new way. He insisted that nature must be studied through careful observation and mathematical analysis, not just through philosophical reasoning. And when his observations contradicted the established wisdom of Aristotle, Galileo trusted what he saw with his own eyes. The famous story says that Galileo climbed to the top of the Leaning Tower of Pisa and simultaneously dropped two balls of different weights. According to Aristotelian physics, the heavier ball should have fallen faster, reaching the ground well before the lighter one. But according to the legend, both balls hit the ground at the same moment, in full view of assembled scholars and students, dramatically disproving Aristotle's theory of falling bodies. It's a wonderful story. It's the kind of demonstration that would make for compelling theater. Unfortunately, it's almost certainly apocryphal. There's no contemporary evidence that Galileo ever performed this particular public demonstration. But while the Tower of Pisa story may be a myth, the conclusion it illustrates is absolutely true. And Galileo did prove it, just not with such dramatic flair. Instead, he used something far more powerful than a single spectacular demonstration. He used careful, repeated experiments that could be precisely measured and mathematically analyzed. The problem with dropping objects from a great height is that they fall too quickly to observe carefully. Even from the top of a tall tower, an object hits the ground in just a few seconds. The motion is too fast to study in detail with the tools available in Galileo's time. So Galileo slowed things down. He built inclined planes, smooth ramps tilted at various angles. Objects rolling down these planes moved more slowly than objects in free fall, slow enough that their motion could be carefully observed and timed. Galileo discovered something remarkable. When he rolled balls of different weights down the same inclined plane, they accelerated at the same rate. If released simultaneously, they reached the bottom at the same moment. It didn't matter whether the ball was made of wood, bronze, or stone. It didn't matter whether it was heavy or light. The acceleration was the same. By adjusting the angle of the plane, Galileo could show that this relationship held true whether the motion was slow on a gentle incline or fast on a steep one. And he reasoned correctly that if the plane were vertical, the motion would become pure free fall, and the result would remain the same. All objects, regardless of their weight, fall at the same rate. This discovery demolished the Aristotelian idea that heavier objects fall faster because they more eagerly seek their natural place. But it raised a new question. If it's not their weight that determines how fast objects fall, what does determine it? Galileo didn't have a complete answer to this question. He could describe how objects fall, mathematically and precisely, but he couldn't fully explain why they fall. He made another crucial discovery. Through careful experiments with balls rolling on very smooth, level surfaces, Galileo demonstrated something that contradicted everyday experience. He showed that a moving object, if not impeded by friction or air resistance, would continue moving indefinitely at the same speed in the same direction. This was the principle of inertia, though Galileo didn't articulate it in quite these terms. It meant that motion didn't require a continuous force to sustain it. An object in motion would naturally stay in motion. Only a change in motion required an explanation. This was a revolutionary insight. For Aristotle, all motion required a mover, a force actively maintaining the motion. For Galileo, motion was the natural state of things. What required explanation was not motion itself, but changes in motion, acceleration. This shift in perspective was subtle but profound. It opened the door to a new physics based on forces that cause changes in motion rather than motion itself. Galileo also turned his telescope toward the heavens, and what he saw there further undermined Aristotelian cosmology. He observed mountains and valleys on the moon, proving it wasn't a perfect, unblemished sphere. He discovered moons orbiting Jupiter, demonstrating that not all celestial bodies orbited the Earth. He observed the phases of Venus, which made sense only if Venus orbited the Sun, not the Earth. The celestial realm, it turned out, was not fundamentally different from the terrestrial realm. The same kinds of matter and motion existed both on Earth and in the heavens. These observations, combined with his experiments on falling bodies, set the stage for a unified physics that could describe both terrestrial and celestial phenomena with the same principles and equations. Galileo didn't complete this unification himself. He made crucial discoveries about how objects move, but he didn't develop a comprehensive theory of what causes the motion, what pulls the apple from the tree, or holds the moon in orbit around Earth. That task would fall to an English mathematician born in the year Galileo died, a man who would synthesize all of these insights into a single powerful framework. That man was Isaac Newton, and his theory of universal gravitation would dominate physics for more than 2 centuries, explaining everything from falling apples to the orbits of distant comets with remarkable precision. It would be the first mathematical description of gravity as a force, and it would work spectacularly well, even though, as we'll see, it couldn't quite be right. Newton and universal gravitation. Isaac Newton was born on Christmas Day in 1642 in the small village of Woolsthorpe in Lincolnshire, England. He was a sickly child, born prematurely, and his father had died before his birth. His early life gave little hint that he would become one of the most influential scientists in history. But Newton possessed a fierce intelligence and an almost obsessive dedication to solving problems. When he focused his formidable mind on the question of why things move as they do, he would revolutionize our understanding of the universe. The famous story, like the Leaning Tower of Pisa story for Galileo, involves a falling apple. According to the legend, Newton was sitting in his garden at Woolsthorpe in 1666, having fled Cambridge to escape an outbreak of plague, when an apple fell from a tree. Watching the apple fall, Newton supposedly had a sudden flash of insight. If the Earth's gravity could reach to the top of a tree and pull the apple down, might it not reach much farther? Might it reach all the way to the moon? Could the same force that causes apples to fall also keep the moon in its orbit around Earth? Unlike the Leaning Tower story, There's some basis for the apple story. Newton himself mentioned it late in his life, though with characteristic modesty he didn't claim it as a sudden revelation, but rather as the beginning of a long process of thought. Whether or not there was actually a specific apple is less important than the profound question it represents. Could the same force that acts locally on everyday objects also act across the vast distances of space to govern the motions of celestial bodies? This question struck at the heart of the Aristotelian division between the terrestrial and celestial realms. For Aristotle, objects on earth fell toward the center because that was the nature of earthly matter, while celestial bodies moved in circles because that was the nature of heavenly matter. But Galileo's telescope had shown that the heavens were made of the same kind of matter as earth, and Galileo's experiments had shown that all objects fall the same way, regardless of what they're made of. Perhaps Newton reasoned, the force causing the apple to fall and the force keeping the moon in orbit were not just similar but identical. Newton had at his disposal several key pieces of information. He knew from Galileo that objects on Earth accelerate downward at a constant rate when dropped, about 9.8 meters per second per second. He knew from Johannes Kepler's laws of planetary motion that planets orbit the sun in ellipses, and that the square of a planet's orbital period is proportional to the cube of its average distance from the sun. And he had developed, simultaneously with the German mathematician Gottfried Leibniz, a powerful new mathematical tool, the calculus, which allowed him to describe and analyze continuously changing quantities. Newton performed a crucial calculation. He computed how fast the moon must be accelerating toward the Earth to remain in its orbit rather than flying off in a straight line. Using the moon's orbital period and its distance from Earth, both of which were known with reasonable accuracy, he could calculate this acceleration. He found it was about 0.027 meters per second. That's much smaller than the 9.8 meters per second that objects experience at Earth's surface, but the moon is much farther from Earth's center than the surface is. The moon orbits at a distance of about 384,000 kilometers from Earth's center, while Earth's surface is only about 670 kilometers from the center. Newton recognized a pattern. The moon is about 60 times farther from Earth's center than the surface is, and the acceleration the moon experiences is about 1/30⁶ of the acceleration at the surface. That's 160 squared. This couldn't be coincidence. The gravitational acceleration, Newton realized, must decrease with the square of the distance from the center of the attracting body. Double the distance, and the acceleration becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. This inverse square relationship was the key. Newton extended it into a complete theory of universal gravitation. Every object with mass, he proposed, attracts every other object with mass. The force of attraction is proportional to the product of the two masses. It's also inversely proportional to the square of the distance between the objects' centers. If you know the masses of two objects and the distance between them, you can calculate exactly how strongly they attract each other. Newton published these ideas in 1687 in his masterwork, Philosophiae Naturalis Principia Mathematica, usually just called the Principia. This work is one of the most important books in the history of science. In it, Newton laid out his 3 laws of motion and his law of universal gravitation. The first law is the principle of inertia. An object at rest stays at rest, and an object in motion continues in a straight line at constant speed unless acted upon by a force. The second law quantifies this. Force equals mass times acceleration. The third law states that for every action, there's an equal and opposite reaction. With these laws and his law of gravitation, Newton could derive Kepler's laws of planetary motion from first principles. He could explain why planets move in ellipses with the sun at one focus. He could explain why they move faster when closer to the sun and slower when farther away. He could explain the paths of comets. He could explain the ocean tides as the result of the moon and sun's gravitational pull on the Earth's waters. He created a unified physics that described the motion of everything from falling apples to distant planets using the same fundamental principles. The success of Newton's theory was extraordinary. Astronomers used it to predict the return of Halley's comet, which had last been seen in 1682. They calculated that it should return in 1758, and it did within the predicted time window. The discovery of the planet Neptune in 1846 was another triumph for Newtonian gravity. Astronomers noticed that the orbit of Uranus didn't quite match the predictions based on the known planets. They hypothesized that an unknown planet beyond Uranus must be perturbing its orbit. Using Newton's law of gravity, they calculated where this unknown planet should be, and when they pointed their telescopes to that region of sky, there it was, Neptune, right where Newton's equations said it should be. For more than 200 years, Newtonian gravity reigned supreme. It worked. It predicted the motions of celestial bodies with remarkable precision. It explained phenomena on Earth and in the heavens with the same mathematical framework. It seemed to be a complete description of how gravity operates. But Newton himself was troubled by one aspect of his theory. His law of universal gravitation states that every mass attracts every other mass, but it doesn't explain how this attraction occurs. The sun, 150 million kilometers away, somehow reaches across the vast emptiness of space to pull on the Earth. But how? How does the sun know the Earth is there? How does the gravitational influence propagate across space? Newton proposed no mechanism. He couldn't. The idea that one object could exert a force on another without any physical contact, without any medium connecting them, seemed almost magical. This problem was known as action at a distance, and it bothered many physicists, including Newton. In the Principia, Newton wrote, "I have not as yet been able to deduce from phenomena the reason for these properties of gravity, and I do not feign hypotheses." He was saying essentially that his theory described how gravity behaves, but not what gravity fundamentally is. It was a mathematical description, not a physical explanation. Gravity acted as if there were an invisible force pulling objects together, but Newton couldn't say what that force actually was, or how it was transmitted across empty space. This limitation didn't prevent Newton's theory from being useful. For practical purposes, for calculating planetary orbits or designing bridges, Newtonian gravity worked perfectly well. But philosophically and physically, it was incomplete, and eventually, as instruments became more precise and observations more detailed, tiny cracks began to appear in the edifice of Newtonian physics. These cracks would ultimately reveal that gravity, as Newton conceived it, couldn't be the whole story. Problems with Newtonian gravity. For most practical purposes, Newton's law of universal gravitation is exactly right. When NASA calculates the trajectory of a spacecraft traveling to Mars, they use Newton's equations. When engineers design buildings and bridges, they use Newtonian physics. For everyday phenomena, and even for most astronomical phenomena, Newton's theory gives the correct answer to as much precision as anyone needs. But precision has its limits, and as the 19th century progressed and measurement techniques improved, astronomers began to notice tiny discrepancies between Newton's predictions and actual observations. The most famous of these involved the planet Mercury, the innermost planet in our solar system. Mercury orbits the Sun in an ellipse, as Newton's theory predicts, but that ellipse itself rotates slowly over time. Imagine drawing an ellipse on a piece of paper, then rotating the paper slightly and drawing the ellipse again. Over centuries, Mercury's orbital ellipse precesses, meaning its orientation gradually changes. The point of closest approach to the Sun, called the perihelion, slowly shifts its position in space. Some of this precession could be explained by Newtonian gravity. The gravitational pull of the other planets, especially Venus and Jupiter, tugs on Mercury and causes its orbit to precess. Astronomers in the 19th century carefully calculated how much precession should occur due to these planetary perturbations. They came up with a number. Mercury's perihelion should precess by about 532 arcseconds per century. An arcsecond is 1/3600th of a degree, so this is a very small effect, less than a sixth of a degree per century. But when astronomers measured the actual precession of Mercury's orbit with increasing precision, they found something puzzling. The observed precession was about 575 arcseconds per century. The difference between the observed value and the calculated Newtonian value was about 43 arcseconds per century. That might sound like a tiny amount, and it is, but it was real and consistent. Mercury's orbit was precessing 43 arcseconds per century, more than Newton's theory could account for. Astronomers tried various explanations. Perhaps there was an undiscovered planet closer to the Sun than Mercury, whose gravitational pull was causing the extra precession. They even gave this hypothetical planet a name, Vulcan. Searches were conducted, but Vulcan was never found. Perhaps the Sun wasn't perfectly spherical, and its slight bulge at the equator was affecting Mercury's orbit, but the calculations didn't work out. Perhaps Newton's law of gravity wasn't exactly an inverse square law, but something slightly different. Perhaps the exponent was 2.216 instead of exactly 2. But this seemed like an arbitrary adjustment, a fudge factor with no theoretical justification. The Mercury anomaly remained unexplained throughout the latter half of the 19th century. It was a small problem, to be sure. 43 arcseconds per century is a minuscule effect, but it was a crack in the edifice, a hint that something about our understanding of gravity wasn't quite right. There was also a deeper, more philosophical problem with Newtonian gravity. Newton's theory describes gravity as an instantaneous force. According to his equations, if the Sun suddenly vanished, the Earth would immediately feel the loss of the Sun's gravitational pull and would fly off in a straight line. The effect would be instantaneous, regardless of the distance. But this seemed to violate basic intuitions about causality. How could an influence propagate across 150 million kilometers of space in zero time? What was the mechanism? In the 19th century, as physicists developed theories of electromagnetism, they discovered that electromagnetic influences don't propagate instantaneously. They travel at the speed of light, about 300,000 kilometers per second. If you suddenly change an electric charge, the effect of that change spreads outward at light speed, not instantaneously. This was incorporated into James Clerk Maxwell's Equations of Electromagnetism, published in the 1860s. Maxwell's equations predicted that electromagnetic disturbances should propagate as waves traveling at the speed of light. And indeed, light itself was revealed to be an electromagnetic wave. This raised an uncomfortable question for Newtonian gravity. If electromagnetic influences propagate at light speed, shouldn't gravitational influences also propagate at some finite speed rather than instantaneously? But Newton's equations had no such limitation built in. They treated gravitational attraction as instantaneous, acting across any distance without delay. This was at odds with the emerging understanding of how forces work in nature. There was also the problem of how gravity fits with the new understanding of space and time that was beginning to emerge. In 1905, Albert Einstein published his special theory of relativity, which showed that space and time are not separate, absolute entities, but are interwoven into a single four-dimensional fabric called spacetime. Special relativity also established that nothing, no influence, no signal, can travel faster than the speed of light. This was a fundamental principle, baked into the structure of spacetime itself, but Newtonian gravity violated this principle. It required instantaneous action at a distance. If the sun suddenly vanished, according to Newton, the Earth would instantly know about it. According to special relativity, it should take at least 8 minutes for the information to travel from the sun to the Earth, because that's how long it takes light to make the journey. The two theories were incompatible. Einstein recognized this problem. Special relativity was elegant and experimentally confirmed, but it only dealt with objects moving at constant velocities, not with acceleration or gravity. Gravity, in the Newtonian framework, was a force that caused objects to accelerate toward each other. How could this be reconciled with the geometry of spacetime described by special relativity? How could gravity be incorporated into this new understanding of space and time? These questions tormented Einstein for nearly a decade after he published Special Relativity. He knew that a more general theory was needed, one that could describe accelerated motion and incorporate gravity into the framework of space-time. The solution he eventually found was so radical, so far removed from Newton's conception, that it fundamentally changed not just our understanding of gravity, but our understanding of reality itself. The key to this revolution was a simple thought experiment, an insight that Einstein would later call the happiest thought of my life. It involved nothing more than imagining what would happen to someone falling freely under gravity. But this simple thought would unlock the secret to understanding what gravity really is, Einstein's path to general relativity. Albert Einstein was sitting in his chair at the patent office in Bern, Switzerland in 1907, wrestling with the problem of gravity. He had published his special theory of relativity 2 years earlier, showing that space and time are relative, that they depend on the observer's state of motion, and that they're woven together into a single space-time fabric. But special relativity only applied to unaccelerated motion, to observers moving at constant velocities. It couldn't handle acceleration, and it couldn't incorporate gravity. Einstein needed something more general. As he later recalled, "Suddenly a thought struck me. If a man falls freely, he would not feel his weight. This simple observation, this thought experiment, was the key that would unlock general relativity. Imagine you're in an elevator and the cable suddenly snaps. As you and the elevator fall together, you float inside the cabin. You feel weightless, just as astronauts do in the International Space Station. If you released an apple, it would float next to you, neither rising nor falling relative to you. In your freely falling reference frame, gravity seems to disappear. This was more than just a curiosity. It was a profound clue about the nature of gravity. Einstein realized that a freely falling observer feels no gravity at all. The person in the falling elevator can't tell by any local experiment performed inside the elevator, whether they're falling in a gravitational field or floating in deep space far from any massive bodies. Both situations feel identical. Both are characterized by the absence of weight, by the ability of objects to float freely without any apparent forces acting on them. Einstein called this insight the equivalence principle, and it would become the foundation of general relativity. The principle states that the effects of gravity are locally indistinguishable from the effects of acceleration. Put another way, being in a gravitational field is equivalent to being in an accelerated reference frame. You can't tell the difference between them by performing local experiments. Let's explore this with another thought experiment. Imagine you're inside a closed room with no windows. You feel your normal weight. You drop a ball, and it falls to the floor. You release a spring, and it extends. Everything behaves as it would on Earth. But are you on Earth standing still in a gravitational field? Or are you in a rocket ship in deep space, far from any gravitating bodies, accelerating upward at 9.8 meters per second per second? Both scenarios would produce identical effects inside your room. The ball falls because the floor is accelerating upward to meet it. The spring extends because it's being accelerated upward. You feel weight because the floor is constantly accelerating upward against your feet. According to the equivalence principle, there's no experiment you can perform inside your windowless room that would tell you which situation you're in. Gravity and acceleration are, in this sense, equivalent. This equivalence isn't perfect when you look at larger regions of space, because gravitational fields aren't perfectly uniform. They vary with position. This variation produces tidal effects, but locally, over small enough regions of space and time, gravity and acceleration are indistinguishable. This insight had profound implications. In special relativity, Einstein had shown that the laws of physics are the same in all inertial reference frames, frames moving at constant velocity relative to each other. But what about accelerated reference frames? The equivalence principle suggested that physics should look the same in these frames too, because an accelerated frame is equivalent to a gravitational field, and gravitational fields are part of nature. Einstein began to work out what this meant for the behavior of light and clocks in gravitational fields. Consider light traveling horizontally across the falling elevator. From the perspective of someone inside the elevator, the light travels in a straight line at constant speed, just as it does in special relativity. But from the perspective of someone watching the elevator fall from outside, the light appears to curve slightly downward because the elevator is accelerating downward while the light crosses it. If gravity and acceleration are equivalent, then light must bend in gravitational fields. This was a testable prediction, radically different from Newtonian gravity, which predicts no bending of light by gravity at all. Newton's theory treats light as massless, and since gravitational force depends on mass, massless light shouldn't be affected by gravity. But Einstein's equivalence principle required that gravity affect everything, including light. Einstein also realized that time must run differently at different gravitational potentials. Imagine two clocks, one on the floor of a tower and one at the top. From the perspective of someone in free fall, both clocks should tick at the same rate, because in free fall, the effects of gravity disappear. But from the perspective of someone standing still on the Earth's surface, the lower clock is deeper in the gravitational field. Einstein showed that the lower clock should tick slightly more slowly than the upper one. Time itself runs slower in stronger gravitational fields. This effect is called gravitational time dilation. These predictions were provocative, but Einstein still didn't have a complete theory. The equivalence principle told him that gravity must be related to the geometry of spacetime. But how? What was the precise mathematical relationship between matter, spacetime, and motion? Working out the details would require Einstein to learn new mathematics, mathematics that didn't come easily to him. In 1912, Einstein returned to Zurich to take a position at the Swiss Federal Institute of Technology, the same institution where he had been a student. He reconnected with his old friend and former classmate, Marcel Grossmann, who was now a professor of mathematics. Einstein explained his ideas to Grossmann and asked for help with the mathematics needed to describe curved spaces. Grossmann introduced Einstein to the mathematics of Riemannian geometry, developed by the German mathematician Bernhard Riemann in the 1850s. This was the tool Einstein needed. Riemannian geometry describes curved spaces of any number of dimensions. In ordinary flat, Euclidean geometry, the sum of angles in a triangle is always 180 degrees. Parallel lines never meet, and the shortest distance between 2 points is a straight line. But on curved surfaces, these rules change. On the surface of a sphere, for instance, the sum of angles in a triangle can exceed 180 degrees. Lines that start out parallel can converge and meet. The straight line, the shortest path between 2 points, is a curve called a geodesic. On a sphere, geodesics are great circles, like the equator or lines of longitude. Einstein realized that gravity might be nothing more than the curvature of spacetime. Massive objects don't pull on other objects across space. Instead, they curve the spacetime around them, and other objects move along the straightest possible paths, the geodesics, through this curved spacetime. The apparent force of gravity is just the effect of objects trying to move in straight lines through a curved geometry. This was a radical reconceptualization. Gravity wasn't a force at all. It was geometry. The presence of mass and energy warps spacetime, and the warping of spacetime tells objects how to move. In the words of physicist John Wheeler, who would later make major contributions to general relativity, matter tells spacetime how to curve, and curved spacetime tells matter how to move. But how exactly does matter curve spacetime? What is the precise mathematical relationship? Einstein struggled with this question for several years. He needed equations that would describe how the distribution of mass and energy determines the curvature of spacetime, and how that curvature in turn affects the motion of matter. These equations needed to reduce to Newton's law of gravity in the limit of weak gravitational fields and slow motion, because Newton's theory worked perfectly well in those regimes. but they also needed to be consistent with special relativity and to produce the new effects that Einstein had predicted, like the bending of light and gravitational time dilation. Einstein tried many different approaches. He made progress, then encountered difficulties, and had to start over. The mathematics was daunting. He was trying to describe a four-dimensional curved space-time, not just a three-dimensional curved space. Time was part of the geometry, and it could be warped just as space could. The equations needed to respect the fundamental symmetry of general relativity, that the laws of physics should look the same in all reference frames, not just inertial ones. Finally, in November 1915, Einstein achieved the breakthrough. He arrived at what are now called the Einstein field equations, a set of 10 interrelated partial differential equations that precisely describe how matter and energy curve spacetime. These equations are elegant but fiendishly complex. They relate the curvature of spacetime, represented by a mathematical object called the Einstein tensor, to the distribution of mass, energy, momentum, and stress, represented by the stress-energy tensor. Einstein presented his field equations to the Prussian Academy of Sciences on November 25, 1915. This date marks the birth of general relativity as a complete theory. Within weeks, Einstein used his new equations to calculate the precession of Mercury's orbit. The equations gave exactly the right answer, 43 arcseconds per century, matching the observations perfectly. This anomaly, which had puzzled astronomers for decades, was immediately explained by general relativity. It wasn't due to an unseen planet or a modification of the inverse square law. It was due to the curvature of spacetime near the Sun, a curvature that became significant for Mercury because Mercury orbits so close to the Sun. This was a stunning success, a powerful confirmation that general relativity was on the right track. But Mercury's orbit was already known. The real test would come with a new prediction, something that hadn't been observed before. Einstein had predicted that light should bend when it passes near a massive object. This could be tested during a solar eclipse, when stars near the Sun's position in the sky become visible. If general relativity was correct, the positions of these stars should appear slightly shifted because their light passing near the Sun would be bent by the Sun's gravitational field. The opportunity to test this prediction would come in 1919, 4 years after Einstein published his theory. But the mathematical framework was now in place. General relativity was complete, and it presented a view of reality radically different from anything that had come before. Gravity wasn't a force transmitted across space. It was the shape of spacetime itself. Spacetime curvature, the new vision of gravity. To understand general relativity, we need to understand what spacetime is and how it can be curved. This requires us to think about space and time in a way that's quite different from our everyday intuitions. In our daily experience, space and time seem separate and absolute. Space is the arena where things happen, the three-dimensional stage on which events play out. Time is the universal clock, ticking away at the same rate for everyone everywhere. But special relativity showed that this picture is wrong. Space and time are not separate. They're interwoven into a single four-dimensional fabric called spacetime. Think of spacetime as a four-dimensional structure where every event has four coordinates, three spatial coordinates that tell you where it happened, and one time coordinate that tells you when it happened. You can't separate the where from the when. They're aspects of the same underlying reality. An event is a point in spacetime, a specific location at a specific moment. The history of an object, as it moves through space and time, traces out a curve in spacetime called a world line. In special relativity, spacetime is flat. By flat, we mean that the rules of geometry are the same everywhere, just as they are on a flat plane. Parallel lines remain parallel forever. The sum of angles in a triangle is 180 degrees. The shortest path between two events is a straight line through space-time, called a geodesic. Objects that aren't acted upon by any forces travel along these straight geodesics through space-time, but general relativity introduces a profound new element. Space-time can be curved. The presence of mass and energy warps the geometry of space-time. Near a massive object like the Sun or the Earth, space-time is no longer flat. It's curved, bent, distorted from its flat geometry. And this curvature is what we perceive as gravity. How does mass curve space-time? The Einstein field equations provide the precise answer, but we can understand the concept through analogy. Imagine space-time as a flexible rubber sheet, stretched out flat. When you place a massive object, like a bowling ball, onto the sheet, it creates a depression, a dip in the sheet's surface. The sheet is no longer flat. It's curved around the bowling ball. Now imagine rolling a marble across the sheet. If the sheet were flat, the marble would travel in a straight line. But with the bowling ball creating a depression, the marble's path curves as it rolls near the bowling ball. It might even be captured in orbit around the bowling ball if its speed and trajectory are right. This rubber sheet analogy has limitations. For one thing, it visualizes the curvature as happening in a third spatial dimension, as if space-time were embedded in some higher dimensional space. But in general relativity, the curvature is intrinsic. It doesn't require any extra dimensions. The curvature is a property of space-time itself, measurable by beings confined to that space-time, without any reference to a higher dimensional embedding space. Also, the rubber sheet analogy only shows the curvature of a two-dimensional space, while space-time is four-dimensional, and it doesn't capture the fact that time, not just space, is part of what gets curved. Nevertheless, the analogy is useful for grasping the basic idea. Mass curves the geometry around it, and that curvature affects the motion of other objects. But how does curvature affect motion? Here's where the beauty of general relativity truly shines. In flat space-time, objects that aren't subject to any forces travel along straight lines at constant speeds. These straight lines are geodesics, the straightest possible paths through space-time. In curved space-time, objects that aren't subject to any forces still travel along geodesics. But geodesics in curved space-time aren't straight lines in the ordinary sense. They're curves. A geodesic is the path of extremal proper time. Proper time is the time measured by a clock carried along with a moving object. In flat space-time, a geodesic is indeed a straight line. But in curved space-time, geodesics can be quite curved when viewed from a distance. Yet from the perspective of the object following the geodesic, it's moving in the straightest possible way. It's not being pushed or pulled by any force. It's simply following the natural geometry of space-time. Consider a planet orbiting the sun. In Newton's view, the planet is being pulled by the sun's gravitational force, which constantly deflects it from a straight line path and keeps it in orbit. But in Einstein's view, there's no force acting on the planet at all. The planet is simply following a geodesic through the curved spacetime around the sun. Because spacetime is curved by the sun's mass, the geodesics near the sun are curved paths that loop around it. The planet is in free fall, just like the person in the falling elevator. It feels no force. It's weightless, moving along the straightest possible path through a curved geometry. This is why astronauts aboard the International Space Station feel weightless. They're not beyond Earth's gravity. The Earth's gravitational field at the station's altitude is still about 90% as strong as at the surface, but the station and the astronauts inside it are in free fall, following geodesics through the curved spacetime around Earth. From their perspective, gravity has vanished. They're moving along the natural force-free paths through space-time. Now, you might ask, if they're in free fall, why don't they crash into the Earth? The answer is that they have horizontal velocity. They're moving sideways fast enough that as they fall, the Earth's surface curves away beneath them at the same rate. Their geodesic is a curved path that circles the Earth without intersecting the surface. It's an orbit, but from the astronaut's perspective, they're simply moving in a straight line through space-time. The straightness of their path in space-time manifests as a curved path in space. This brings us to an important point. When we talk about objects following geodesics in curved space-time, we're talking about their motion through four-dimensional space-time, not just through three-dimensional space. An object at rest on the Earth's surface is actually accelerating through space-time because the ground is constantly pushing it upward, preventing it from following its natural geodesic. The feeling of weight, the sensation of the ground beneath your feet, is the sensation of being pushed off a geodesic, of being accelerated away from free fall. This is a complete inversion of the Newtonian picture. In Newton's theory, you feel your weight because gravity is pulling you down, and the ground is resisting that pull. In Einstein's theory, you feel your weight because the ground is pushing you up, accelerating you away from the geodesic you would naturally follow. Gravity isn't pulling you down. The ground is pushing you up. When you step off a ledge and begin to fall, you're not being pulled downward by a force. You're returning to your natural state of motion, following a geodesic through space-time. The sensation of falling, the stomach-dropping feeling, is the sensation of transitioning from an accelerated state, standing on the ground, to an inertial state, free fall. In free fall, you feel nothing. No forces act on you. You're weightless, following the straightest possible path through the geometry of space-time. The curvature of space-time is described mathematically by the metric tensor, a mathematical object that encodes distances and angles in the curved geometry. The Einstein field equations relate this metric tensor to the distribution of mass and energy. Solving these equations for a given distribution of matter tells you what the geometry of space-time looks like, how it's curved. Once you know the geometry, you can calculate geodesics, and those geodesics tell you how objects will move. For example, Carl Schwarzschild solved Einstein's equations in 1916 for the case of a spherically symmetric mass, like a star or planet. The resulting geometry is now called the Schwarzschild geometry. It describes how space-time is curved around an isolated, non-rotating spherical mass. In this geometry, you can calculate the geodesics, and you find that they reproduce the elliptical orbits, predicted by Newton's theory, but with small corrections. One of those corrections is the precession of Mercury's orbit, which comes out exactly right. But the Schwarzschild geometry also predicts something Newton's theory doesn't. The geometry becomes increasingly distorted as you get closer to the mass, and if the mass is compressed into a small enough volume, the geometry becomes so distorted that a region forms from which nothing, not even light, can escape. This is a black hole, a prediction we'll explore in detail later. The curvature of spacetime also affects time, not just space. Clocks run slower in stronger gravitational fields, as Einstein predicted from the equivalence principle. This is gravitational time dilation, and it's a direct consequence of the curvature of time as well as space. Near a massive object, time itself is stretched, distorted. A clock placed on the surface of the Earth ticks slightly more slowly than a clock placed far from any massive bodies. The difference is tiny for Earth's gravity, only about 1 part in a billion, but it's real and measurable. This time, dilation has practical consequences. The Global Positioning System, GPS, relies on precise timing signals from satellites orbiting Earth. These satellites carry atomic clocks that must be synchronized with clocks on the ground to an accuracy of better than a microsecond. But because the satellites are higher in Earth's gravitational field than the ground-based clocks, general relativity predicts that the satellite clocks will run faster by about 45 microseconds per day. If this effect weren't corrected for, GPS would accumulate errors of several kilometers per day, making it useless. The engineers who designed GPS had to account for general relativity. Every time you use GPS to navigate, you're relying on Einstein's theory of curved spacetime. The curvature of spacetime also bends the paths of light rays. Light travels along geodesics too, but they're null geodesics, paths through spacetime that correspond to zero proper time, because light travels at the speed of light and experiences no passage of time. In curved spacetime, these null geodesics are curved paths. Light passing near a massive object is deflected, bent by the curvature of spacetime around that object. This bending of light is one of the most famous predictions of general relativity, and it was the first one to be tested observationally. The amount of deflection depends on how close the light passes to the massive object and how massive the object is. For light grazing the sun's surface, general relativity predicts a deflection of about 1.75 arcseconds, roughly 1,000th of a degree. This is twice the deflection predicted if you naively apply Newtonian gravity to light, treating light as if it were made of particles with mass. The factor of 2 comes from the curvature of time as well as space. General relativity presents a universe that's fundamentally geometric. Gravity isn't a force transmitted through space, it's the shape of spacetime itself. Matter and energy tell spacetime how to curve. Curved spacetime tells matter and energy how to move. Objects in free fall aren't subject to any forces. They're following the natural geodesic paths through the curved geometry of spacetime. The sensation of weight, the feeling of being pulled by gravity, is actually the sensation of being pushed, of being prevented from following your natural path through spacetime. This is the deep insight at the heart of general relativity. Gravity is geometry. And once you grasp this idea, once you understand that objects aren't being pulled by an invisible force, but are simply following the contours of curved space-time, you begin to see the universe in a fundamentally different way. But this revolutionary theory was just that, a theory, until it could be tested against observation. The true vindication of general relativity would come from experiments that confirmed its predictions, predictions that differed from those of Newton's theory. The first of these tests would take place on an island off the coast of Africa during a total solar eclipse in 1919. Experimental confirmations. A theory, no matter how elegant or mathematically beautiful, must face the tribunal of experiment. General relativity made specific testable predictions that differed from Newtonian gravity. If those predictions were confirmed, Einstein's theory would be validated. If they were contradicted, the theory would have to be abandoned or modified. The first major test came just a few years after Einstein published his field equations. Einstein had predicted that light passing near the sun would be bent by the sun's gravitational field, by which we now mean the curvature of spacetime around the sun. The amount of bending depends on how close the light passes to the sun's surface. For light grazing the limb of the sun, the deflection should be about 1.75 arcseconds. This is a very small angle, but it's measurable with careful astronomical observations. The problem is that you can't normally see stars near the sun in the daytime sky. The sun's glare overwhelms the faint starlight, but during a total solar eclipse, when the moon blocks the sun's disk, stars near the sun's position become visible. If you photograph the stars during an eclipse and compare their positions to their positions when the sun is elsewhere in the sky, you can measure any apparent shift in their positions. That shift, if it exists, would be due to the bending of their light as it passes near the sun. The opportunity to test this prediction came on May 29, 1919, when a total solar eclipse would be visible from parts of South America and Africa. The British astronomer Arthur Stanley Eddington organized 2 expeditions to observe the eclipse, one to the town of Sobral in Brazil, and another to the island of Principe off the west coast of Africa. Eddington led the Principe expedition himself. The goal was to photograph stars near the sun during totality and measure their positions with high precision. The observations were challenging. The expeditions had to set up their equipment in remote locations with uncertain weather. They had to take the photographs during the brief minutes of totality when the moon completely covered the sun's disk, and they had to achieve photographic precision sufficient to measure shifts of less than 2 arcseconds. Weather conditions at Sobral were good, and the team there obtained excellent photographs. At Principe, Eddington's team faced clouds and managed only a few usable images. Back in England, Eddington and his colleagues analyzed the photographic plates. They measured the positions of stars on the eclipse, photographs, and compared them to positions measured on photographs taken months earlier when the sun was in a different part of the sky. They found that the stars appeared shifted, displaced outward from the sun's limb, exactly as general relativity predicted. The amount of shift matched Einstein's prediction to within the errors of measurement. The deflection was about 1.75 arcseconds, not the 0.87 arcseconds predicted by a Newtonian calculation, treating light as if it consisted of massive particles. The results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6, 1919. The physicist J.J. Thomson, president of the Royal Society, called it one of the highest achievements of human thought. Newspapers around the world carried the story. Headlines proclaimed that Newton had been overthrown and that a new understanding of the universe had emerged. Overnight, Einstein became a global celebrity, the most famous scientist in the world. This confirmation of general relativity was a triumph, but it was just the beginning. In the century since Eddington's expedition, general relativity has been tested in countless ways, with ever-increasing precision, and it has passed every test. Mercury's orbit provided another early confirmation. We've already mentioned that general relativity correctly accounts for the 43 arcseconds per century anomalous precession of Mercury's perihelion. This was actually the first observational evidence in favor of general relativity, even before the eclipse measurements. Newton's theory couldn't explain this precession without invoking unseen planets or modifications to the inverse square law. General relativity explained it naturally, as a consequence of the curvature of spacetime near the Sun. Gravitational redshift was another prediction. Einstein had shown that time runs slower in stronger gravitational fields. This means that light emitted from a source in a strong gravitational field will be redshifted, its wavelength stretched toward the red end of the spectrum when observed by someone in a weaker field. The effect is small for the Sun or Earth, but it's measurable. The first precise test of gravitational redshift came in 1959 with an experiment by physicists Robert Pound and Glenn Rebka at Harvard University. They used the Mossbauer effect, a technique involving gamma rays emitted by radioactive iron atoms, to measure tiny frequency shifts. They placed a gamma ray source at the top of a 22.5-meter tower and a detector at the bottom. General relativity predicted that the gamma rays, climbing out of Earth's gravitational field as they rose, should be slightly blue shifted when they reached the top. Alternatively, gamma rays emitted at the top and detected at the bottom should be red shifted as they descended into the stronger field at the base. Pound and Rebka measured exactly this effect. The frequency shift was only about 2 parts in a trillion, but it matched Einstein's prediction precisely. This experiment has since been repeated with greater precision using atomic clocks at different altitudes, and the agreement with general relativity is now confirmed to about 1 part in 100,000. Gravitational time dilation has been measured directly by comparing atomic clocks at different altitudes. In one famous experiment, physicist Joseph Eiffel and astronomer Richard Keating flew atomic clocks around the world on commercial airliners in 1971, comparing them to reference clocks that remained stationary. The flying clocks experienced less gravitational time dilation because they were at higher altitude, and they also experienced time dilation due to their velocity, as predicted by special relativity. When all the effects were accounted for, the measured time differences agreed with relativity's predictions to within experimental error. GPS satellites provide a continuous test of both special and general relativity. The satellites orbit at an altitude of about 20,000 kilometers, where Earth's gravitational field is weaker than at the surface. General relativity predicts that clocks on the satellites should run faster than clocks on the ground by about 45 microseconds per day due to gravitational time dilation. But the satellites are also moving at about 14,000 kilometers per hour relative to the ground, and special relativity predicts that moving clocks run slower. This effect causes the satellite clocks to lose about 7 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. GPS engineers must correct for this relativistic time dilation. The satellite clocks are programmed to tick at a slightly slower rate than they would naturally, so that when viewed from the ground, they appear to tick at the correct rate. Without these corrections, GPS would accumulate errors of several kilometers per day. The fact that GPS works is a daily confirmation that both special and general relativity are correct. More exotic tests have been performed using pulsars, rapidly rotating neutron stars that emit beams of radio waves. Some pulsars are in binary systems, orbiting around another neutron star or a white dwarf companion. The orbital motion of these pulsars can be tracked with extraordinary precision by timing the arrival of their radio pulses. Deviations from a constant pulse rate reveal the orbital motion and allow astronomers to measure the orbits with incredible accuracy. In some of these systems, general relativity predicts effects like the precession of the orbit's orientation, analogous to Mercury's perihelion precession, but much larger. It also predicts that the system should lose energy by emitting gravitational waves, causing the orbit to gradually shrink. These predictions have been tested in systems like the Hulse-Taylor binary pulsar, discovered in 1974, and they match general relativity's predictions to within a fraction of a percent. The orbital decay of this system provided the first indirect evidence for gravitational waves, decades before they were directly detected. In 2004, NASA launched Gravity Probe B, a satellite designed to test two subtle predictions of general relativity. The first, called the geodetic effect, is the amount by which spacetime is curved by Earth's mass. The second, called frame dragging, is the effect of Earth's rotation on the surrounding spacetime. General relativity predicts that a rotating mass should drag spacetime around with it, like a spinning ball in honey. Gravity Probe B carried 4 ultra-precise gyroscopes in orbit around Earth. The orientations of these gyroscopes should gradually change due to the geodetic effect and frame dragging by amounts that could be calculated from general relativity. The experiment was extraordinarily difficult. The predicted drifts were tiny, only about 6 arcseconds per year for the geodetic effect, and 0.04 arcseconds per year for frame dragging. The gyroscopes had to be the most perfect spheres ever made, and they had to be kept isolated from any forces other than gravity. After years of data analysis, the results were announced in 2011. Both effects were confirmed, matching Einstein's predictions to within the experimental errors. More recently, astronomers have observed extreme gravitational effects around black holes and neutron stars. Neutron stars have masses comparable to the Sun, but radii of only about 10 kilometers, making them incredibly dense. The gravitational field, or space-time curvature, near their surfaces is immense. Light emitted from their surfaces is significantly redshifted. X-rays from gas falling onto their surfaces show effects of extreme time dilation and light bending. These observations match general relativity's predictions for such strong field environments. Perhaps the most visually striking confirmation came in April 2019, when the Event Horizon Telescope collaboration released the first image of a black hole, the supermassive black hole at the center of the galaxy M87. This black hole has a mass about 6.5 billion times that of the Sun. The image showed a bright ring of emission surrounding a dark central region. This is exactly what general relativity predicts. The dark region is the black hole's shadow, the area from which no light can escape because spacetime is so severely curved that all paths lead inward. The bright ring is emission from hot gas orbiting the black hole at near light speed. The shape and size of the shadow matched the predictions of general relativity precisely. All of these tests, from the 1919 eclipse to the 2019 black hole image, have confirmed general relativity. The theory has been tested in weak gravitational fields, like those around Earth, moderate fields like those around the Sun, and extreme fields like those around neutron stars and black holes. It has been tested for slow-moving objects and for objects moving at significant fractions of light speed. It has been tested over distances from meters in laboratory experiments to billions of light years in cosmological observations. And in every case, general relativity has proven accurate. This doesn't mean the theory is final or complete. There are realms where general relativity is expected to break down, particularly at the quantum scale or in the singularities, at the centers of black holes. But within its domain of applicability, general relativity is one of the most precisely tested and most successful theories in all of physics. Its central insight, that gravity is the curvature of spacetime, has been confirmed over and over again. And this curvature of spacetime leads to some of the most fascinating and extreme phenomena in the universe. When spacetime is curved just a little, you get planetary orbits and the bending of starlight. But when spacetime is curved extremely, when mass is compressed into small volumes and the curvature becomes intense, you get objects so bizarre that they challenge our understanding of reality itself. You get black holes, extreme spacetime, curvature. Black holes represent the ultimate expression of general relativity's central insight. They are regions where spacetime is curved so intensely that nothing, not even light, can escape. They're places where the fabric of reality becomes so warped that the usual rules seem to break down. And they exist. They're not just theoretical curiosities. We've observed them, measured them, and in 2019 we even photographed one. To understand black holes in the context of general relativity, we need to understand what happens when spacetime curvature becomes extreme. Remember that in general relativity, gravity is curvature. The more mass you compress into a given volume, the more severe the curvature becomes. For normal objects like the Earth or Sun, the curvature is mild. Spacetime is only slightly warped, and its effects, while measurable, are small. But as you increase the mass or decrease the size of an object, the curvature grows stronger. Carl Schwarzschild found the first exact solution to Einstein's field equations in 1916, just months after Einstein published the theory. Schwarzschild was a German physicist serving on the Eastern Front during World War I when he worked out his solution. He was interested in the geometry of spacetime around a perfectly spherical, non-rotating mass like an idealized star. His solution described how spacetime curves in the region outside such a mass. The Schwarzschild solution contains a remarkable feature. There's a critical radius, now called the Schwarzschild radius, at which something dramatic happens to the geometry. For any mass, you can calculate this radius. For the Sun, it's about 3 kilometers. For the Earth, it's about 9 millimeters. These radii are much smaller than the actual sizes of these objects. So the exotic behavior at the Schwarzschild radius isn't relevant for normal stars and planets. But imagine compressing the Sun down to a sphere 3 kilometers in radius, or the Earth down to a marble 9 millimeters across. If you could do this, something extraordinary would happen. The space-time curvature at the surface would become so extreme that the escape velocity would equal the speed of light. Any object at that radius would have to travel at light speed to escape to infinity. Since nothing can travel faster than light, nothing at or inside this radius can escape. This radius defines the event horizon of a black hole. It's not a physical surface, not a barrier made of matter. It's a purely geometric feature of space-time, a point of no return in the geometry. If you fall past the event horizon, you can never escape. All future paths, all geodesics, starting from inside the horizon, lead inward to the center. There's no way out, not even in principle. The geometry of space-time itself forbids it. At the very center of the Schwarzschild geometry, at radius 0, there's a singularity. This is a point where the curvature of space-time becomes infinite, where the equations of general relativity break down. The singularity is not a place in the usual sense. It's more like an edge or boundary of space-time, a place where space-time itself ceases to exist in its normal form. What happens at the singularity is unknown. General relativity can't tell us. Most physicists suspect that a quantum theory of gravity, a theory that combines general relativity with quantum mechanics, would be needed to describe what really happens there. The Schwarzschild solution describes a non-rotating black hole, but real black holes formed from the collapse of rotating stars or built up through accretion would naturally possess angular momentum. In 1963, the New Zealand mathematician Roy Kerr discovered the solution to Einstein's equations for a rotating black hole. The Kerr solution is considerably more complex than Schwarzschild's. A rotating black hole drags space-time around with it in a phenomenon called frame dragging, much like how a spinning object in honey would drag the fluid along. The event horizon of a Kerr black hole is smaller than that of a non-rotating Schwarzschild black hole of the same mass. And there's an additional region outside the event horizon called the ergosphere, where space-time is dragged around so strongly that nothing can remain stationary. Everything in the ergosphere must rotate with the black hole, whether it wants to or not. For most of the 20th century, black holes were regarded as fascinating theoretical possibilities, but not necessarily real objects. Could nature actually produce them? The answer came from understanding stellar evolution. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. If the star is sufficiently massive, more than about 20 to 25 times the sun's mass, the core collapses catastrophically. The outer layers are blown off in a supernova explosion, but the core continues to collapse. Nothing can stop it. Electron pressure can't stop it. Neutron pressure can't stop it. The core collapses all the way down past its Schwarzschild radius and forms a black hole. By the 1960s and 1970s, astronomers began finding evidence for black holes in binary star systems. If a normal star orbits an invisible massive companion, and if matter from the normal star flows toward the companion, that matter should heat up to millions of degrees as it swirls into a disk around the companion. This hot matter should emit X-rays. And indeed, astronomers found X-ray binary systems with these characteristics. The most famous is Cygnus X1, an X-ray source in the constellation Cygnus. It consists of a normal blue supergiant star orbiting an invisible object with a mass of about 15 times the Sun. That's too massive to be a neutron star. It must be a black hole. Over the decades, Astronomers have identified dozens of stellar mass black holes in our galaxy, each with masses between about 5 and 20 times the Sun. They've also discovered supermassive black holes at the centers of galaxies. These monsters have masses ranging from millions to billions of times the Sun. The Milky Way's central black hole, Sagittarius A star, has a mass of about 4 million solar masses. The black hole at the center of M87, the one imaged by the Event Horizon Telescope, has a mass of about 6.5 billion solar masses. The question of how these supermassive black holes formed remains one of the active areas of research in astrophysics. Several formation mechanisms have been proposed. They could have grown gradually by accreting gas and swallowing stars over billions of years. They might have formed from the merger of smaller black holes that gradually combined into larger ones. Or they could have formed directly in the early universe from the collapse of massive gas clouds, bypassing the stellar phase entirely. Current observations suggest that different supermassive black holes may have formed through different pathways, and the relative importance of these mechanisms is still being investigated. What we can say with certainty is that these objects are real and play crucial roles in galaxy evolution. The Event Horizon Telescope image of M87's black hole, released in April 2019, was a watershed moment. For the first time, humanity saw the shadow of a black hole, the dark region from which no light can escape. The image showed a bright ring of emission, light from gas orbiting just outside the event horizon at nearly the speed of light. The size and shape of the shadow matched the predictions of general relativity precisely. Here was direct visual evidence that these objects exist and that they behave as Einstein's equations predict. Since that first image, the EHT has also imaged Sagittarius A star, the black hole at the center of our own galaxy, and more images are coming. Each one provides a new test of general relativity in the most extreme gravitational environments accessible to observation. Black holes also provide testing grounds for exotic predictions of general relativity. One is Hawking radiation, predicted by Stephen Hawking in 1974. Hawking combined general relativity with quantum mechanics to show that black holes should not be perfectly black. According to his calculations, they should emit a faint thermal radiation due to quantum effects near the event horizon. The temperature of this radiation is inversely proportional to the black hole's mass. For stellar mass black holes, the predicted temperature is incredibly small, far colder than the cosmic microwave background, so they would absorb more radiation than they emit. But for hypothetical tiny black holes, if they exist, the Hawking radiation could be significant and might even cause them to evaporate over time. Hawking radiation has never been directly observed because it would be so faint for astrophysical black holes. However, the prediction is widely accepted by physicists as theoretically sound, and it has profound implications. It suggests that black holes have entropy, that they encode information in some way. This leads to what's known as the black hole information paradox, a deep puzzle about what happens to information that falls into a black hole. Does it disappear forever, which would violate fundamental principles of quantum mechanics? Or is it somehow preserved and eventually released in the Hawking radiation? This question remains one of the biggest unsolved problems in theoretical physics, at the intersection of quantum mechanics and general relativity. Black holes are also sources of gravitational waves, ripples in space-time itself. When two black holes orbit each other, they emit gravitational waves, losing energy and gradually spiraling closer together. Eventually, they merge in a cataclysmic event that releases enormous amounts of energy in the form of gravitational waves. These waves spread outward through space-time at the speed of light, carrying information about the event that created them. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves from a black hole merger. This detection opened a new window on the universe, a new way of observing cosmic phenomena, and it provided yet another confirmation of general relativity. The observed gravitational wave signal matched the theoretical predictions derived from Einstein's equations for two black holes spiraling together and merging. Gravitational waves from black hole mergers have now been detected dozens of times. Each detection teaches us more about black holes, about how they form and evolve, and about the nature of space-time itself. And each one confirms that general relativity accurately describes even the most violent and extreme events in the cosmos. Black holes are the ultimate demonstration that gravity is geometry. They're regions where space-time is curved so severely that it creates horizons, boundaries in space-time beyond which nothing can return. They challenge our intuitions about space and time. They push general relativity to its limits and beyond, to regimes where quantum effects must eventually become important. They're fascinating, exotic, and deeply strange. And they're real, out there in the universe, warping space-time in the most extreme ways possible. And they're not the only exotic prediction of general relativity. The theory also predicts that accelerating masses should create ripples in the fabric of space-time, waves of curvature that propagate through space at the speed of light. These are gravitational waves, and their detection represents one of the greatest experimental achievements in the history of physics. Gravitational waves, ripples in space-time. If space-time is a dynamic, flexible fabric that can be curved by mass and energy, then it stands to reason that it can also ripple, that disturbances in space-time can propagate outward as waves. This is exactly what general relativity predicts. Gravitational waves are ripples in the curvature of space-time, traveling at the speed of light, produced by the acceleration of massive objects. Einstein predicted the existence of gravitational waves in 1916, shortly after publishing his field equations. He showed that when masses accelerate, they create changes in the gravitational field that can't propagate instantaneously. Instead, the changes spread outward at light speed as waves in space-time itself. These waves alternately stretch and squeeze space in perpendicular directions as they pass through. Imagine a gravitational wave traveling toward you. As it arrives, it will stretch space in one direction, say left-right, while squeezing it in the perpendicular direction up-down. Then it will reverse, squeezing left-right and stretching up-down. This oscillation continues as the wave passes by. The effect is incredibly small. Even for the most violent events in the universe, like colliding black holes or exploding stars, the gravitational waves that reach Earth stretch and squeeze space by only a tiny fraction. A wave from a black hole merger, a billion light years away, might change the distance between 2 points, separated by 4 kilometers, by less than 1/10,000th the diameter of a proton. This is an almost unimaginably small effect. For most of the 20th century, gravitational waves were regarded as a theoretical prediction that could probably never be detected directly, but there was indirect evidence. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar, a system in which two neutron stars orbit each other. One of the neutron stars is a pulsar, emitting regular pulses of radio waves with extraordinary precision. By timing these pulses, Hulse and Taylor could track the orbital motion of the pulsar with incredible accuracy. They found that the orbit was gradually shrinking. The two neutron stars were spiraling closer together. This orbital decay matched exactly the prediction of general relativity for a system losing energy through the emission of gravitational waves. Over decades of observation, the agreement between the observed orbital decay and the theoretical prediction became more and more precise. This was compelling evidence that gravitational waves exist and carry energy away from accelerating masses, even though the waves themselves hadn't been directly detected. Hulse and Taylor were awarded the Nobel Prize in Physics in 1993 for this discovery. Meanwhile, physicists and engineers were working on instruments that might directly detect gravitational waves. The basic idea is to use an interferometer, a device that splits a laser beam and sends the two halves down perpendicular arms, each several kilometers long. The beams bounce off mirrors at the ends of the arms and return to be recombined. If the arms' lengths are exactly equal, the beams interfere constructively, producing a bright signal. But if a gravitational wave passes through, it will alternately stretch one arm while squeezing the other, changing their relative lengths and causing the interference pattern to change. Building such an instrument is extraordinarily difficult. The length changes you're trying to measure are smaller than a proton's diameter over distances of kilometers. Every vibration, every seismic rumble, every passing truck creates noise that could swamp the tiny gravitational wave signal. The mirrors must be exquisitely smooth and precisely positioned. The laser must be stable. The whole apparatus must be isolated from environmental disturbances as much as possible. The Laser Interferometer Gravitational Wave Observatory, LIGO, was conceived in the 1980s by physicists Rainer Weiss, Kip Thorne, and Ronald Drever. It consists of two identical detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers. Each detector has two arms, each 4 kilometers long, arranged in an L shape. Construction began in the 1990s, and the initial LIGO began taking data in 2002. But the first generation detectors weren't sensitive enough. No gravitational waves were detected during the first observing runs. Between 2010 and 2015, LIGO underwent a major upgrade to advanced LIGO, increasing its sensitivity by a factor of about 10. The improved detectors came online in September 2015, and almost immediately they made a historic detection. On September 14, 2015, at 9:45 UTC, both LIGO detectors registered a signal. It lasted about 1/5 of a second, sweeping upward in frequency from 35 Hz to about 250 Hz. The signal looked exactly like the theoretical prediction for two black holes spiraling together and merging. The event was designated GW150914 for gravitational wave and the date. Analysis of the signal revealed that it came from two black holes with masses of about 36 and 29 times the Sun, located about 1.3 billion light-years away. As they spiraled together, they emitted gravitational waves, losing orbital energy and spiraling closer and closer. In the final fraction of a second, they merged into a single black hole of about 62 solar masses. The missing 3 solar masses, about 3% of the total, were converted into energy and radiated away as gravitational waves, following Einstein's E equals mc squared. For a brief moment, this merger released more power than all the stars in the observable universe combined, though all in gravitational waves rather than light. The detection was announced on February 11, 2016, to worldwide acclaim. It was the first direct observation of gravitational waves, confirming a century-old prediction of general relativity. It was also the first direct observation of a binary black hole merger, proving that such systems exist. And it opened a new era in astronomy, a new way of observing the universe. For this discovery, Weiss, Thorne, and Barish, who led the LIGO project, were awarded the Nobel Prize in Physics in 2017. Since that first detection, LIGO has been joined by other gravitational wave detectors. The Virgo detector in Italy came online in 2017. The Kagra detector in Japan began observations in 2020. Together, these detectors form a global network that can not only detect gravitational waves, but also pinpoint their sources in the sky by comparing the arrival times at different detectors. As of early 2026, the LIGO-Virgo-Kagra collaboration has detected gravitational waves from hundreds of events. Most are from black hole mergers, but a few are from neutron star mergers or from mixed systems where a black hole merges with a neutron star. Each detection provides a new test of general relativity. The observed waveforms match the theoretical predictions with extraordinary precision. The waves propagate at the speed of light, as Einstein predicted. The polarization of the waves matches the predictions. General relativity passes every test. One particularly important detection occurred on August 17, 2017. LIGO and Virgo detected gravitational waves from a neutron star merger designated GW17817. Crucially, this event was also detected by gamma-ray telescopes as a short gamma-ray burst, and then by optical telescopes as a kilonova, a faint explosion powered by the radioactive decay of heavy elements synthesized in the merger. This was the first multi-messenger observation combining gravitational waves with electromagnetic radiation. The timing was crucial. The gravitational waves and the gamma rays arrived within 1.7 seconds of each other after traveling 130 million light years. This proved that gravitational waves travel at the speed of light to within 1 part in a quadrillion. It also constrained alternative theories of gravity. Any theory that predicts gravitational waves travel at a different speed from light is ruled out by this observation. The neutron star merger also produced heavy elements, including gold and platinum. The observation of the kilonova confirmed that neutron star mergers are major sources of heavy elements in the universe. It was a synthesis of astrophysics, nuclear physics, and gravitational physics, all enabled by the detection of gravitational waves. Gravitational wave astronomy is still in its infancy, but it's already revolutionizing our understanding of the universe. Future detectors will be even more sensitive. The Laser Interferometer Space. Antenna LISA is planned for launch in the 2030s. It will be a space-based detector consisting of 3 spacecraft flying in formation, separated by 2.5 million kilometers, and will detect gravitational waves at lower frequencies than ground-based detectors can. LISA will be sensitive to supermassive black hole mergers, to the early in-spiral of stellar mass black holes years before they merge, and possibly even to gravitational waves from the Big Bang itself. The Einstein telescope and Cosmic Explorer are proposed next generation ground based detectors that would be 10 times more sensitive than current instruments. They could detect black hole mergers across the entire observable universe and neutron star mergers out to cosmological distances. They would observe thousands of events per year, turning gravitational wave astronomy into a precision science. Gravitational waves are perhaps the most direct confirmation that spacetime is a real physical entity that can ripple and flex. They're not vibrations of some medium filling space. They are vibrations of space itself. They demonstrate that spacetime is as real and tangible as any material substance, something that can carry energy and information, something that can be disturbed and set oscillating. They're ripples in the fabric of reality itself, and they provide a window into regions of spacetime so extreme, so violently curved that no other form of radiation can escape. Black hole mergers are completely dark in electromagnetic waves. You can't see them with optical telescopes or X ray telescopes, but you can hear them with gravitational wave detectors. You can listen to the song of spacetime as two black holes spiral together, the increasing pitch as they accelerate, the final merger, and the ring down as the resulting black hole settles into a quiescent state. General relativity predicted all of this. It predicted that spacetime could wave, that these waves would travel at light speed, that they would carry energy, that they would be produced by accelerating masses, and every prediction has been confirmed. Gravitational waves are real, and their detection stands as one of the greatest experimental achievements in the history of science, a triumph of human ingenuity and persistence in measuring effects so small they were once thought impossible to detect. But for all its successes, general relativity is not the final theory of gravity. There are realms where it's expected to break down, where its predictions become unreliable or even nonsensical. These are the realms of the very small, the quantum realm, where the smooth fabric of space-time, envisioned by Einstein, must somehow mesh with the probabilistic, discrete nature of quantum mechanics. This is the domain of quantum gravity, and it remains one of the greatest unsolved problems in physics, the quantum problem and modern mysteries. General relativity and quantum mechanics are the two great pillars of modern physics. General relativity describes gravity, space-time, and the large-scale structure of the universe. Quantum mechanics describes atoms, particles, and the behavior of matter and energy at the smallest scales. Both theories have been tested extensively and have proven extraordinarily successful within their domains. General relativity works perfectly for planets, stars, galaxies, and the expansion of the universe. Quantum mechanics works perfectly for atoms, molecules, subatomic particles, and the forces between them. But the two theories don't work together. They are, in their current forms, fundamentally incompatible. And this incompatibility isn't just an aesthetic problem. There are situations where both theories should apply, where gravity is strong and quantum effects are important. At the centers of black holes, for instance, where matter is compressed to infinite density at a singularity, quantum mechanics must become relevant. In the first moments of the Big Bang, when the entire universe was smaller than a subatomic particle, quantum effects and gravitational effects must have been equally important. To understand these extreme conditions, we need a theory that combines general relativity and quantum mechanics into a single, coherent framework. We need a theory of quantum gravity. Why don't general relativity and quantum mechanics fit together? The incompatibility runs deep, involving the fundamental structures of the two theories. General relativity is a classical theory. It treats spacetime as a smooth, continuous fabric. Physical quantities like the curvature of spacetime have definite values at every point. The theory is deterministic. If you know the distribution of matter and energy at one time, you can in principle calculate the geometry of spacetime and the motion of objects at all future times. Quantum mechanics is different. It's probabilistic, not deterministic. Physical quantities like the position or momentum of a particle don't have definite values until they're measured. Before measurement, the particle exists in a superposition of possible states. Quantum mechanics also introduces a fundamental graininess to nature. Energy comes in discrete packets called quanta. Angular momentum is quantized. Even space and time might be quantized at the smallest scales, though we don't yet know this for sure. When physicists try to apply the techniques of quantum mechanics to gravity, treating the gravitational field as they would treat the electromagnetic field or other forces, they run into problems. They try to construct a quantum field theory of gravity in which spacetime curvature would be described by quantum fields, and gravitational interactions would be mediated by particles called gravitons, analogous to how electromagnetic interactions are mediated by photons. This approach works beautifully for the other forces. Quantum electrodynamics, the quantum theory of electromagnetism, is one of the most precisely tested theories in all of science. But when you try to apply the same approach to gravity, the mathematics breaks down. The theory produces infinities, nonsensical predictions that can't be removed by the standard techniques used in quantum field theory. Physicists say the theory is non-renormalizable. This doesn't necessarily mean quantum gravity is impossible, but it does mean that treating gravity as just another quantum field using the same methods that work for other forces doesn't work. Something more profound is needed. Why is gravity different? One reason might be that gravity is geometry. In quantum mechanics, you typically have quantum fields living in a fixed space-time background. But in general relativity, space-time itself is dynamic, shaped by matter and energy. If space-time is quantized, you lose the fixed background. The stage on which quantum mechanics usually plays out becomes a quantum actor itself. This background independence is a fundamental feature of general relativity, and incorporating it into quantum mechanics is a major challenge. Another issue is the nature of time. In quantum mechanics, time is a parameter, something that flows uniformly and is measured by clocks. In general relativity, time is part of space-time, something that can be warped and stretched by gravity. There's no universal time. Different observers in different gravitational fields experience time differently. Reconciling these two views of time is profoundly difficult. Despite these challenges, physicists have been working on quantum gravity for decades, pursuing several different approaches. The most well-known is string theory. In string theory, the fundamental constituents of nature aren't point particles, but tiny vibrating strings of energy. Different vibration modes of these strings would correspond to different particles we observe. One of the vibrational modes behaves mathematically like a graviton, the hypothetical particle that would mediate gravitational interactions in a quantum theory. String theory naturally incorporates gravity in a way that avoids some of the infinities that plague other approaches to quantum gravity. But string theory comes with its own significant challenges. The mathematics requires extra spatial dimensions beyond the familiar three of space and one of time. The theory is mathematically consistent in 10 or 11 dimensions, and these extra dimensions must somehow be hidden or compactified in a way that's consistent with our four-dimensional experience. String theory has also proven difficult to test experimentally. The energy scales where its distinctive features would become directly observable are far beyond what current or foreseeable particle accelerators can reach, making experimental verification extraordinarily challenging. Additionally, there are many different versions of string theory, what physicists call the landscape of string solutions, making it difficult to extract specific testable predictions about the universe we inhabit. Another approach is loop quantum gravity. This approach takes general relativity's background independence seriously and attempts to quantize spacetime itself. In loop quantum gravity, space is not treated as a smooth continuum, but as a network of discrete quantum loops and nodes. The theory suggests that space might come in discrete chunks, that there could be a smallest possible unit of volume and area, though this remains to be confirmed experimentally. This quantization of geometry might resolve the singularities predicted by classical general relativity, potentially replacing infinities with finite, albeit extremely large, curvatures. Loop quantum gravity has had some theoretical successes. It suggests that black hole singularities might be replaced by what theorists call a quantum bounce, where the collapsing matter doesn't compress to infinite density but reaches some maximum density and then rebounds, potentially creating a new region of space-time. The theory also provides a quantum mechanical description of black hole entropy, linking the entropy to the number of quantum states associated with the horizon's geometry. However, loop quantum gravity faces significant challenges as well. Researchers are still working to show conclusively how classical general relativity emerges smoothly from the theory in the limit of large distances and low energies. And like string theory, it has not yet produced many concrete, testable predictions that could be verified with current technology. There are other approaches as well. Causal sets treat spacetime as a discrete collection of events with causal relationships. Asymptotic safety posits that gravity might be renormalizable, after all, under certain conditions. Emergent gravity theories suggest that spacetime and gravity might not be fundamental, but might emerge from some deeper, more fundamental theory, much as thermodynamics emerges from statistical mechanics. All of these approaches are works in progress. None has yet provided a complete tested theory of quantum gravity. And in the absence of experimental guidance, it's hard to know which approach, if any, is on the right track. The energy scales where quantum gravitational effects are expected to be important are far beyond what we can probe with current technology. We can't build particle accelerators powerful enough to create quantum black holes or to probe the structure of spacetime at the Planck scale, about 10 to the minus 35 meters, where quantum gravity effects should become significant. This lack of experimental guidance is a major obstacle. Science progresses through the interplay of theory and experiment. Theories make predictions, experiments test them, and the results guide the development of new theories. But for quantum gravity, we have theories, but no experiments, no observations that can decisively tell us which theories are correct and which are wrong. It's like trying to navigate without a map or compass. There are, however, some potential observational windows. Observations of the early universe through the cosmic microwave background radiation or through primordial gravitational waves might carry signatures of quantum gravitational effects from the Big Bang. Certain processes involving black holes, like Hawking radiation or the information paradox, might provide clues. There's even speculation that effects of quantum gravity might show up in subtle ways in high energy cosmic rays or in the behavior of particles near black holes. And then there are the mysteries of dark matter and dark energy. Observations from galaxy rotation curves, gravitational lensing, and the cosmic microwave background indicate that the universe contains substantially more matter than we can directly observe through electromagnetic radiation. This dark matter interacts gravitationally, but doesn't emit or absorb light in any part of the electromagnetic spectrum we've measured. Its fundamental nature remains unknown. Leading candidates include new types of subatomic particles that interact only weakly with ordinary matter. Though despite extensive searches, no dark matter particles have been conclusively detected in laboratory experiments. Whether dark matter is related to quantum gravity or represents something else entirely is an open question. Dark energy presents an even deeper mystery. Observations of distant supernovae in the late 1990s revealed something unexpected. The expansion of the universe is accelerating rather than slowing down, as would be expected from gravity alone. This acceleration requires something that counteracts gravity's attractive influence on cosmic scales. This phenomenon has been attributed to dark energy, which appears to make up about 68% of the total energy content of the universe. Its fundamental nature is completely unknown. It could be the energy of empty space itself, related to what Einstein called the cosmological constant. It could be a new field permeating space, dynamically changing over time. Or it could indicate that general relativity breaks down on the largest cosmological scales, requiring a modification of Einstein's equations. Current observations favor the cosmological constant explanation, but alternative theories remain actively investigated. Some physicists have proposed modified theories of gravity as alternatives to the dark matter hypothesis. The most well-developed is modified Newtonian dynamics, or MOND, which proposes that Newton's laws of gravity and motion behave slightly differently at very low accelerations, such as those found in the outer regions of galaxies. MOND can reproduce some features of galaxy rotation curves without invoking dark matter. However, MOND faces significant challenges in explaining other observations. It struggles to account for the behavior of galaxy clusters, the patterns observed in gravitational lensing, and the detailed structure of the cosmic microwave background radiation. Perhaps most importantly, MOND has not been successfully incorporated into a fully relativistic theory consistent with general relativity and its many confirmed predictions. As a result, while MOND remains an interesting alternative hypothesis that continues to be explored by some researchers, the majority of physicists favor the view that dark matter represents actual matter we simply haven't detected directly yet, rather than a modification of gravitational laws. The nature of dark matter and dark energy remains one of the biggest open questions in physics. Resolving these mysteries may require new physics beyond general relativity and the standard model of particle physics, or it may simply require discovering and understanding new forms of matter and energy within our existing theoretical frameworks. Either way, these questions sit at the frontier of our understanding of the universe. General relativity has been tested extensively and has passed every test, but we know it can't be the final theory. It breaks down at singularities, places where its predictions become infinite and meaningless. It doesn't incorporate quantum mechanics, which we know is essential for understanding the microscopic world, and it may not fully explain dark matter and dark energy, which dominate the universe's mass energy budget. The quest for quantum gravity, for a theory that unifies general relativity and quantum mechanics, continues. It's one of the great challenges of modern physics, and solving it will require not just brilliant mathematics and careful observation, but also conceptual leaps, new ways of thinking about space, time, matter, and reality itself. It may require abandoning some cherished assumptions, accepting ideas that seem strange or counterintuitive, and venturing into intellectual territory that's truly unknown. But the journey is worthwhile. Understanding quantum gravity would complete the unification of physics that began with Newton, continued through Maxwell and Einstein, and remains unfinished today. It would give us a complete theory of how the universe works, from the smallest subatomic scales to the largest cosmic scales. It would tell us what happened in the first moments of the Big Bang, what lies at the heart of black holes, and perhaps even what lies beyond our universe. It would be one of the greatest intellectual achievements in human history, and it would deepen our understanding of what gravity truly is. We've come so far from the Aristotelian idea that heavy objects fall because they seek their natural place. We've moved beyond Newton's mysterious action at a distance. We understand now that gravity is not a force, but the curvature of spacetime. But there's still more to learn. Gravity's relationship with quantum mechanics, its behavior at the smallest scales, its ultimate nature. These questions remain open, and answering them will take us even deeper into the heart of reality. Implications and conclusion. We've traveled a long road tonight, from ancient Greece to the frontiers of modern physics. We've seen how humanity's understanding of gravity evolved, from Aristotle's natural motion to Newton's universal force to Einstein's curved space-time. We've explored the evidence for general relativity, the predictions it makes, and the observations that confirm it. We've ventured into the extreme realms of black holes and gravitational waves, and we've glimpsed the challenges that lie ahead, the quest to unify gravity with quantum mechanics and to understand the deepest mysteries of the cosmos. But let's step back and reflect on what we've learned. The central insight of general relativity is that gravity is not a force. This is not just a technical detail, a different way of doing the same calculations. It's a profound reconceptualization of what gravity is and how it works. Gravity is geometry. It's the shape of space-time itself. Mass and energy curve space-time, and that curvature guides the motion of objects. Objects in free fall aren't being pulled by a force. They're following the straightest possible paths through a curved geometry. This insight changes how we think about the universe. It tells us that space and time are not absolute, unchanging backdrops against which events play out. They're dynamic, flexible, responsive to the presence of matter and energy. The fabric of reality can be stretched, compressed, warped, and rippled. Space-time is as physical and real as any material substance. It also tells us that the sensation of weight, the feeling of being pulled toward the ground, is actually the sensation of being pushed, of being accelerated away from free fall by the ground beneath our feet. When you stand on the earth, you're not being pulled downward by a force. You're being pushed upward, prevented from following your natural geodesic through space-time. The ground is accelerating you upward at 9.8 meters per second, and you feel this acceleration as weight. This inversion of perspective can be disorienting. It challenges our intuitions, but it's the correct understanding, confirmed by a century of observations and experiments. And it has profound implications for how we understand causality, motion, and the structure of reality. General relativity also reveals that time is not absolute. It flows differently in different gravitational fields. A clock on the ground runs slower than a clock high in the mountains, and the difference is measurable. Time itself is part of the geometry that's warped by mass and energy. This means that simultaneity is relative. Events that are simultaneous for one observer might not be for another. The universe doesn't have a single universal now. Instead, each observer has their own experience of time, shaped by their motion and by the gravitational fields they're in. These insights have philosophical implications too. They challenge the classical notion that space and time are containers, empty boxes that exist independently of the contents they hold. In general relativity, space-time is not a container. It's part of the physical world, shaped by matter and energy, influencing and influenced by everything in the universe. The geometry of space-time is as much a part of physics as the motion of particles or the propagation of light. General relativity also reveals a universe that's far stranger and more diverse than Newton could have imagined. It predicts black holes, regions where space-time curvature becomes so extreme that nothing can escape. It predicts gravitational waves, ripples in space-time that carry energy and information across the cosmos. It predicts the expansion of the universe, the Big Bang, the possibility that the universe had a beginning in time and may have an end. All of these predictions have been confirmed by observation, but general relativity is not the end of the story. We know it's incomplete. It doesn't incorporate quantum mechanics. It predicts singularities where its own equations break down. It may not fully explain dark matter and dark energy. The quest for a more complete theory, a quantum theory of gravity, continues. This quest will likely require us to revise our understanding of space-time yet again, to discover new principles and structures deeper than anything we currently know. Yet even in its current form, general relativity stands as one of the greatest achievements of human thought. It's a testament to what the human mind can accomplish when it combines imagination, mathematical rigor, and respect for experimental evidence. Einstein didn't have access to particle accelerators or space telescopes. He worked with pencil and paper, thought experiments, and mathematical equations. And yet he uncovered a truth about the universe so profound that it reshaped our entire understanding of space, time, and gravity. This journey from Newton to Einstein, from force to geometry, illustrates how science progresses. It doesn't move in a straight line. It involves false starts, puzzles, anomalies that don't fit the prevailing theories. But through persistence, creativity, and careful observation, science advances. Old theories are not simply discarded. They're seen as approximations, valid in certain regimes, but incomplete. Newton's theory of gravity still works perfectly well for launching satellites or planning space missions. It's accurate enough for almost all practical purposes, but it's nested within the larger framework of general relativity, which extends to regimes where Newton's theory breaks down. And someday, general relativity itself may be nested within an even larger framework, a quantum theory of gravity that extends to regimes where general relativity breaks down. This is how science works. Each generation builds on the insights of the previous one, extending our understanding into new realms, uncovering deeper truths about the nature of reality. Tonight, you've learned that gravity is not a force, it's the curvature of spacetime. Objects fall not because they're being pulled, but because they're following the natural geometry of the universe. The ground beneath your feet is pushing you upward, preventing you from following your natural path through space-time. Black holes are not massive objects pulling everything in, but regions where space-time is so curved that all paths lead inward. Gravitational waves are not vibrations in some medium, but ripples in the fabric of space-time itself. This understanding changes how you see the world. When you drop a ball and watch it fall, you're witnessing the curvature of space-time. When you feel your weight, you're feeling the acceleration of the ground pushing you away from free fall. When you look up at the night sky and see the moon, you're seeing an object following a geodesic through curved space-time, tracing its eternal path around the Earth. The universe is far stranger, far more beautiful than we ever imagined, and we've only begun to understand it. General relativity has opened windows onto realms we couldn't have dreamed of a century ago. Black holes, gravitational waves, the expanding universe, the warping of time itself. All of this is real, part of the universe we inhabit. And there's more to discover. Dark matter, dark energy, quantum gravity, the ultimate fate of the universe. These mysteries await. Science is not a collection of facts. It's an ongoing conversation between humanity and nature. We ask questions through experiments and observations. Nature answers through the phenomena we observe, and we refine our understanding, building theories that make sense of those phenomena and predict new ones. This process never ends. There will always be more to discover, deeper questions to ask, new puzzles to solve. Thank you for joining me on this journey through one of the most profound ideas in all of science. If you found this exploration meaningful, if it changed how you see the universe and your place within it, please consider liking and subscribing to the channel. Your support helps me continue making these deep dives into the nature of reality. And remember, every time you feel your weight, every time you see something fall, you're experiencing not a force, but the geometry of the universe itself. You're part of the curved space-time, following your world line through the four-dimensional fabric of reality. That's what gravity is. Not a force pulling you down, but the shape of the universe telling you how to move. It's geometry. It's beautiful. And it's real. Good night.